This is the third video in the sequence on problem-solving strategies with electrostatic forces. In the first sequence, you were shown how to create a free body diagram given some stationary charged objects. And in the second sequence, you were shown how to create a vector diagram based on your free body diagram. In this third video, we'll be modeling the problem-solving approach you could use, how to analyze your vector diagram to determine the net electric force acting on a charged object. Now there's some background knowledge that you'll bring to the table. We are presuming you're familiar with Coulomb's law and that you either have or can create a vector diagram. Now remember, once you have a vector diagram, you actually have two choices available to you. You could analyze each vector and break it into its components, that is in the east-west direction or the north-south direction. Or instead, you could use the sine and cosine law to solve the problem, and that works best if your vector diagram is in the form of a triangle. Now remember, as you go through a screencast illustrating problem-solving strategies, the way to get the most out of it is to pause the video at the appropriate time. Try to do the calculations yourself and then continue with the video, treat it as an answer key, and see if you've learned from the process. So I'll model that today as we go through one problem together. And I'll illustrate all of the three steps that are presented in these screencasts, although the first two stages I'll, of course, reduce or skim over a little bit because they were expanded in detail in the other videos. So the problem we're going to work on together is the positive 30 microcoulomb charge shown down here at the bottom. Our challenge is to find the net electric force on it due to the other two charges. And that is a negative charge up here and a positive charge up here. So just conceptually, as I'm presented with this, the first thought that goes in my head is that there's going to be an attractive force pulling this 30 microcoulomb charge up towards the negative 10 microcoulomb charge. And there will be a repulsive force down towards the southeast, I guess, acting on this 30 microcoulomb charge due to the positive 40 microcoulomb charge. So that's just in the back of my head as I begin to digest the problem. So we get a little bit more formal. Our first step was to create a free body diagram. So we'll draw the vectors more carefully this time. So first we'll consider the positive 30 and the negative 10 microcoulomb charge. There will be an attractive force upwards, pulling that 30 microcoulomb charge up, and I've labeled it Fe sub 10, so I don't mix it up with any other forces. The second situation I'll deal with is the positive 40 microcoulomb charge, and that will produce a repulsive force down to the southeast, and I've labeled that force Fe sub 40. Now the relative size of those two vectors we've already gone through in depth in the first screencast, and if you're unfamiliar with that, I suggest you go back to take a look at it. Now that we have a free body diagram labeling our two forces, we have to go to the next step, which is create a vector diagram based on our free body diagram. So to do that, we're going to add the two vectors tip to tail. So we'll move one vector up. And now the net force, which will be from where we started to where we finished in our vector diagram, will complete our triangle in this case. So the vector diagram now becomes our key tool for analysis, and that's what we're going to focus on. Now, while we have the situation like this, it might help to look for patterns in geometry that can simplify. So for example here, the angle theta given in the diagram with the distances between the charges would be an alternate interior angle to the between the two forces in the vector diagram. So that may be helpful for us to see those patterns first. So before we move on, let's calculate that angle. So because we have a right angle triangle, we can use the tangent function. The opposite side is 4 meters long. The adjacent side is 3 meters long. So if you do the calculation along with us, you should be able to confirm that the angle theta would be 53 degrees. So we can replace that in our vector diagram as you see here. I've moved our original situation with the charges down to the right-hand side, just as a reference for us. But really, it's the vector diagram up at the top of the page that we're really going to be paying attention to. So a good place to pause the video right now. Do the calculations yourself to try to find, up at the top, the electric force due to the 10 microcoulomb charge and the electric force due to the 40 microcoulomb charge. Once you've completed those two calculations, then resume the video. So, welcome back. If we're going to determine the electric force due to the 10 microcoulomb charge, we'll apply Coulomb's law, shown here. And our substitution, a step at a time, K is 9 times 10 to the 9th, so that's substitution. And next, the two charges we're working with. We have the 10 microcoulomb charge and the 30 microcoulomb charge. Notice I've left them both as just positive values. We're determining the magnitude of the electric force here. So I'm not putting in a negative value for the negative 10 charge. The distance between them is 3 meters. Complete your calculation. We have 0.3 newtons as the electric force. I can replace that in my vector diagram now as we work through the problem. Hopefully you got that right. Let's try the second one. So the electric force due to the 40 microcoulomb charge, our substitution of Coulomb's constant, the two charges, 40 and 30 microcoulombs. The distance between them in this case now is 5 meters. Don't forget to square the distances. As you put this all in your calculator, see if you agree with the solution, 0.32 newtons. So again, we can put this in our vector diagram, easier to picture now, and we're ready to solve for the net electric force. So at this point, again, I would suggest pausing the video, take a few moments, calculate the net electric force acting on this charge, and once you have a solution, then resume the video and see if you got it right. So welcome back. Now the calculation for the net electric force, we will use the cosine law, and that means we have to sum the square of the two sides. So that's 0.432 and 0.3. We square those. We have to subtract 2 times the product of those two sides and multiply it by the cosine of the angle between the two sides. If you complete the calculation through for the net electric force, if you haven't made a mistake, you should get 0.348 newtons as the net electric force. Now don't forget, forces are vectors. That means there must be a direction associated with the force. In this case, I've labeled it as alpha. So now to calculate alpha, probably the most convenient way is to use the sine law. So we set up our arrangement, make our substitution for the angles and the opposite sides. We know that theta will be 53 degrees. The opposite side we've calculated, that is the net electric force. Alpha is unknown. The side across from it is 0.432 newtons. So when we do our calculation, we end up with an angle of 83 degrees. So if you did the calculation correctly, hopefully you agree. Now that 83 degrees is measured from the north. So when we do our presentation here, this 83 degrees is going to be to the east of north. Or you could treat it instead and say we're at 6.9 degrees north of east. So either one would be fine in presenting your final solution. Now I've got a computer simulation that illustrates this, this experiment. So let's see if we can confirm our results with the simulation. So we're focusing again on the charge down at the bottom of the diagram. And just before we go any further, notice the solution here presented is 0.34 newtons. So that does match with our solution, at least to 2 significant figures. And as we continue on, notice the path that this charge follows. It is slightly to the north of east. Although we don't have the value presented in the simulation, we can see it approximately corresponds to an angle of, say slightly less than 10 degrees north of east. So we have some verification of our solution, and we've gone through one advanced Coulomb's law problem together. So I hope as you continue on with your work in electrostatics, you can use our problem-solving strategies as a model. So let's just summarize those, because this has been in 3 separate videos. What should you do when you're presented with a series of static charges? So first, you do need to apply Coulomb's law. So remember, KQQ over D squared. Q needs to be in coulombs. Be careful of those micro or nano units. D needs to be in meters. The Coulomb's constant, 9 times 10 to the 9th. And the problem-solving strategy, remember, no matter what, go through these 3 steps. First, a free body diagram, paying attention to the relative size and direction of each vector that you draw. And that may take a little bit more work, but if you do it, you'll have better intuition as you work through your problems together. Second, draw a vector diagram and make sure you include the net force vector in your diagram. Now, depending upon how complex the situation is, you may have to analyze the problem by components, or if conveniently it forms a triangle, then your vector diagram can be analyzed using the sine and cosine law. I hope that helped. Good luck, Continue with your practice on Coulomb's law, and our next screencast is on electric fields.